I have never met a man so ignorant that I could not learn something from him. Galileo Galilei. The Infinite Cosmos, A Journey Beyond the Stars. Introduction, The Immensity of the Universe. In the vastness of space, where light travels millions of years before reaching the eyes of an observer, we find ourselves on a small, seemingly insignificant world, Earth. Yet, despite our apparent smallness, we are graced with the capacity to contemplate the cosmos, to ask profound questions, and to seek answers that lie far beyond our own existence. The universe is not just a collection of stars and galaxies, it is a grand narrative in which we play a part, a story that began billions of years ago with the birth of space and time. Humanity has always looked to the skies for answers. From ancient stargazers who saw constellations as divine symbols, to modern astronomers peering through powerful telescopes, our understanding of the universe has expanded, but so too has our sense of awe. Each discovery, each new cosmic revelation, only deepens the mystery of our existence and the vastness of the universe. The immensity of the universe is beyond human comprehension. Stretching across billions of light-years, with more stars than grains of sand on all the beaches of Earth, the cosmos is a place of endless wonder and mystery. Yet, despite its scale, it invites us to explore, to question, and to discover our place within it. Carl Sagan once said, "We are star stuff," and indeed, the atoms that make up our bodies were forged in the hearts of ancient stars. The universe is not something outside of us, it is within us, and we are part of its story. This journey will take us through the birth of the universe, the formation of galaxies and stars, the intricate dance of planets, and the search for life beyond Earth. Along the way, we will explore the most profound questions humanity has ever asked: where did we come from? What is our place in the cosmos? And are we alone in the universe? Chapter 1, The Birth of the Universe. The Big Bang, the genesis of everything. In the beginning, there was nothing. No time, no space, no matter. And then, in an instant, everything changed. The universe was born in a moment of unimaginable energy and heat, a singularity from which all of existence exploded outward. This event, known as the Big Bang, marks the origin of the cosmos as we know it. At that moment, approximately 13.8 billion years ago, the universe began to expand at an incredible rate, creating the fabric of space and time. It was a moment of pure creation, where the laws of physics themselves were forged. Within the first fractions of a second, the universe was a hot, dense soup of particles, quarks, electrons, and photons, swirling in a chaotic dance. As the universe cooled, these particles began to combine, forming protons and neutrons, and eventually, the first atoms. The Big Bang was not an explosion in space, it was an explosion of space. Every point in the universe was once contained within that singularity, and as it expanded, it carried everything with it. The galaxies we see today are not moving through space, they are being carried along by the expansion of space itself. This fundamental truth reshapes our understanding of the cosmos, revealing that the universe is not static, but dynamic, always growing, always changing. The cosmic microwave background. As the universe continued to expand and cool, it reached a point, roughly 380,000 years after the Big Bang, when light could finally travel freely through space. Before this moment, the universe was opaque, a dense fog of particles that scattered photons in every direction. But as temperatures dropped, electrons began to bind with protons, forming the first hydrogen atoms, and the universe became transparent. The light from this era, known as the cosmic microwave background, CMB, is the oldest radiation we can observe. It is a snapshot of the universe as it was in its infancy. The CMB is a faint glow that fills the entire universe, a relic of the Big Bang that has traveled through space for billions of years. It provides us with a direct window into the early universe, allowing us to study the conditions that existed just moments after the birth of time. The tiny fluctuations in temperature and density that we observe in the CMB are the seeds from which galaxies and stars would eventually form. These small variations tell the story of how the universe evolved from a uniform state to the complex cosmic structure we see today. Dark matter and dark energy, the unseen forces. As we gaze into the cosmos, we find that much of it remains hidden from view. The stars and galaxies we observe with our telescopes make up only a small fraction of the universe. The rest, nearly 95%, is composed of dark matter and dark energy, mysterious forces that we cannot see or directly detect but whose presence is felt throughout the cosmos. Dark matter is an invisible substance that exerts a gravitational pull on galaxies, holding them together and preventing them from flying apart. Without dark matter, galaxies as we know them could not exist. It forms the scaffolding upon which the visible universe is built, shaping the distribution of galaxies and the large-scale structure of the cosmos. Yet, despite its profound influence, we still do not know what dark matter is. It does not emit, absorb, or reflect light, making it detectable only through its gravitational effects. Even more enigmatic is dark energy, a force that is driving the expansion of the universe to accelerate. While gravity works to pull matter together, dark energy pushes the universe apart, causing galaxies to recede from one another at an ever-increasing rate. This discovery has revolutionized our understanding of the cosmos, revealing that the universe's expansion is not slowing down, as once thought, but is speeding up. The nature of dark energy remains one of the greatest mysteries in modern physics, a challenge that may hold the key to understanding the ultimate fate of the universe. Chapter 2, Galaxies, Islands in the Cosmic Ocean. The universe is a sea of galaxies, each one a colossal collection of stars, planets, gas, and dark matter, held together by the force of gravity. Galaxies are the basic building blocks of the universe's structure, scattered like islands across the vast cosmic ocean. Some are small and faint, home to a few million stars, while others, like the Milky Way, contain hundreds of billions of stars. Despite their immense distances from one another, these galaxies are interconnected, forming massive clusters and superclusters, linked by vast filaments of dark matter that stretch across space. Galaxies come in many shapes and sizes. Some are elegant spirals, with arms of stars and gas winding around a central bulge. Others are elliptical, smooth and featureless, with stars orbiting in random directions. There are also irregular galaxies, chaotic and disordered, shaped by the gravitational influences of their larger neighbors. But regardless of their form, each galaxy tells the story of cosmic evolution, the forces that have shaped the universe since its earliest days. Formation of galaxies, a cosmic puzzle. The formation of galaxies is one of the great mysteries of astrophysics. Shortly after the Big Bang, the universe was a relatively uniform sea of gas and dark matter. But over time, small fluctuations in density, seeded by quantum fluctuations during the universe's infancy, began to grow. These tiny variations, observed today in the cosmic microwave background, acted as the gravitational seeds from which galaxies would eventually form. As these fluctuations grew larger, they began to collapse under their own gravity, pulling in gas and dark matter. The process of galaxy formation was chaotic and violent, with gas clouds colliding, heating up, and fragmenting into smaller clumps. Within these clumps, the first stars were born, igniting nuclear fusion in their cores and lighting up the universe for the first time. Over billions of years, these early star-forming regions merged and grew, forming the galaxies we see today. The shape and size of a galaxy depend on many factors: the amount of gas available for star formation, the influence of nearby galaxies, and the mysterious presence of dark matter, which acts as a gravitational anchor, holding galaxies together. The Milky Way, our cosmic home. The Milky Way is the galaxy we call home, a majestic spiral structure with arms that stretch across 100,000 light-years of space. It contains not only stars but also vast clouds of gas and dust, the raw materials for future star formation. At its heart lies a supermassive black hole, millions of times the mass of our Sun, which exerts a powerful gravitational influence on the surrounding stars and gas. Our solar system is located in one of the Milky Way's spiral arms, about 26,000 light-years from the galactic center. From our vantage point on Earth, we see the Milky Way as a faint, glowing band of light stretching across the night sky, the combined light of billions of distant stars. The Milky Way is part of a larger structure known as the Local Group, a collection of about 54 galaxies, including the Andromeda Galaxy, which is on a collision course with the Milky Way. In about 4 billion years, the two galaxies will collide, merging to form a new, larger galaxy. While such a collision might seem cataclysmic, the vast distances between stars mean that very few stars will actually collide. Instead, the galaxies will pass through one another, their stars and gas clouds interacting gravitationally, triggering waves of new star formation. Supermassive black holes, the dark hearts of galaxies. At the center of nearly every large galaxy lies a supermassive black hole, a region of space where gravity is so intense that not even light can escape. These black holes are millions, sometimes billions, of times the mass of the Sun, and they play a crucial role in the formation and evolution of galaxies. Supermassive black holes are thought to form from the collapse of massive clouds of gas in the early universe. As they grow, they consume nearby matter, pulling in gas, dust, and even entire stars. This material forms a swirling disk around the black hole, heating up as it spirals inward and emitting intense radiation. These active black holes can outshine entire galaxies, producing quasars, some of the most luminous objects in the universe. But supermassive black holes also regulate star formation within galaxies. The energy they release can heat up the surrounding gas, preventing it from collapsing to form new stars. This feedback mechanism is essential for explaining why some galaxies, despite containing vast amounts of gas, produce very few new stars. Without the influence of their central black holes, galaxies might have evolved very differently. Galactic collisions, the dance of the universe. Galaxies are not isolated entities, they are constantly interacting with one another, pulled together by their mutual gravity. When galaxies collide, the result is a spectacular cosmic dance that reshapes both participants. Stars are flung into new orbits, gas clouds collide and compress, and new generations of stars are born in brilliant bursts of light. One of the most famous examples of a galactic collision is the antennae galaxies, two interacting galaxies that are in the process of merging. As their stars and gas clouds collide, they produce vast regions of star formation, lighting up the galaxies like a cosmic fireworks display. Over time, the two galaxies will merge into a single, larger galaxy, their individual structures lost in the chaos of the collision. Our own Milky Way is set to collide with the Andromeda Galaxy in about 4 billion years. Although the stars in both galaxies are unlikely to collide directly, the gravitational forces will warp their shapes, pulling stars into new orbits and triggering bursts of star formation. Eventually, the two galaxies will merge, forming a giant elliptical galaxy, erasing the spiral structure of both. Galactic collisions are not rare in the universe. In fact, they are a natural part of the cosmic evolution. Most galaxies we see today have experienced multiple mergers over their lifetimes, and these interactions have played a key role in shaping the galaxies we observe. Without galactic collisions, the universe would be a very different place. Chapter 3, Stars, the Beacons of the Cosmos. If galaxies are the islands of the universe, then stars are their brilliant beacons, lighting up the cosmic ocean with their energy. Stars are the most fundamental building blocks of galaxies, the sources of light and heat that make life possible. They are born in vast clouds of gas, live for billions of years, and die in spectacular explosions, scattering their elements across the universe. The story of stars is the story of the universe itself. They are the furnaces where the elements are forged, the creators of planets and the potential harbingers of life. In their lifetimes, they evolved through a series of stages, from their fiery birth in stellar nurseries to their dramatic deaths as supernovae or quiet ends as white dwarfs. The light from distant stars carries the history of the universe, allowing us to peer back in time and study the cosmos as it once was. The life and death of stars. Stars are born from the collapse of dense regions within giant molecular clouds, regions of space filled with gas and dust. As these regions collapse under their own gravity, they heat up, eventually reaching the temperatures and pressures necessary to ignite nuclear fusion in their cores. This process, which fuses hydrogen into helium, releases immense amounts of energy, causing the star to shine. Stars spend most of their lives in a stable phase known as the main sequence, during which they fuse hydrogen into helium in their cores. The length of time a star spends on the main sequence depends on its mass. Smaller stars, like red dwarfs, can burn for trillions of years, while massive stars, many times the mass of the Sun, burn through their fuel in just a few million years. As a star exhausts its hydrogen fuel, its core contracts and heats up, igniting the fusion of heavier elements. For stars like the Sun, this marks the beginning of the red giant phase, where the outer layers of the star expand and cool, creating a large, luminous star. In the final stages of a low-mass star's life, it sheds its outer layers, forming a beautiful cloud of gas known as a planetary nebula. The remaining core becomes a white dwarf, a dense, slowly cooling remnant of the once brilliant star. Massive stars, however, end their lives in a much more violent manner. When a massive star's core can no longer support the fusion of heavier elements, it collapses under its own gravity, triggering a supernova explosion. This explosion releases more energy in a few seconds than the Sun will emit in its entire lifetime, and it scatters the star's outer layers into space, enriching the surrounding gas with elements like carbon, oxygen, and iron, elements essential for life. Supernovae, cosmic fireworks. Few events in the universe are as spectacular and awe-inspiring as a supernova. When a massive star exhausts its nuclear fuel, its core collapses in on itself, triggering a colossal explosion that can outshine entire galaxies. These explosions, known as supernovae, are the death throes of massive stars, but they are also acts of creation. Supernovae play a vital role in enriching the cosmos with heavy elements, such as iron, gold, and uranium. These elements, forged in the intense heat and pressure of the explosion, are scattered across space, where they become the building blocks of planets and, eventually, life. In this sense, we are all the children of supernovae, born from the remnants of ancient stars. Supernovae also create some of the most exotic objects in the universe, neutron stars and black holes. When a massive star explodes, its core can collapse into a neutron star, an incredibly dense object made almost entirely of neutrons. A neutron star is so dense that a single teaspoon of its material would weigh as much as a mountain on Earth. Some neutron stars become pulsars, emitting beams of radiation that sweep across the cosmos like a cosmic lighthouse. In the most extreme cases, the core of a collapsing star can form a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. Black holes are among the most mysterious and fascinating objects in the universe, warping the fabric of space and time around them. The study of black holes has opened up new realms of physics, challenging our understanding of the cosmos and the nature of reality itself. Supernovae are rare events, occurring once every 100 years or so in a galaxy the size of the Milky Way. Yet, despite their rarity, they have a profound impact on the universe, shaping galaxies, creating elements, and influencing the evolution of life. Without supernovae, the universe as we know it would not exist. Exoplanets, the search for other worlds. For much of human history, the idea of other worlds orbiting distant stars was the stuff of speculation and imagination. But in recent decades, the discovery of exoplanets, planets beyond our solar system, has transformed our understanding of the universe and our place in it. We now know that planets are not rare, they are common. Nearly every star in the sky likely has at least one planet, and many of these planets are potentially habitable. The search for exoplanets began in earnest in the 1990s with the discovery of the first planet orbiting a Sun-like star. Since then, thousands of exoplanets have been discovered, ranging from gas giants many times the size of Jupiter to rocky, Earth-like worlds that may harbor liquid water. These discoveries have been made using a variety of techniques, including the transit method, which detects the slight dimming of a star's light as a planet passes in front of it, and the radial velocity method, which measures the tiny wobble of a star caused by the gravitational pull of an orbiting planet. One of the most exciting aspects of the search for exoplanets is the possibility of finding life beyond Earth. While most exoplanets discovered so far are too hot, too cold, or too massive to support life as we know it, a growing number of Earth-sized planets have been found in the habitable zone, the region around a star where conditions might be just right for liquid water to exist. Water is considered a key ingredient for life, and the discovery of habitable zone planets has raised the tantalizing possibility that life may exist elsewhere in the universe. The search for life on exoplanets is still in its infancy, but the next generation of telescopes, including the James Webb Space Telescope, promises to revolutionize our ability to study distant worlds. These telescopes will be able to analyze the atmospheres of exoplanets, searching for chemical signatures that might indicate the presence of life, such as oxygen, methane, and other biosignatures. As we continue to search for other worlds and the potential for life beyond Earth, we are reminded of how interconnected we are with the cosmos. The discovery of even the simplest life forms on another planet would have profound implications for our understanding of life, the universe, and our place within it. We are part of a much larger cosmic story, one that stretches across time and space, and the search for exoplanets is one of the ways we are beginning to uncover that story. Chapter 4, The Solar System, Our Cosmic Home. Our solar system is but one of billions in the Milky Way galaxy, yet it is special to us because it is our home. The Sun, a middle-aged star, lies at the center, providing the energy that sustains life on Earth. Around the Sun orbit 8 planets, numerous moons, dwarf planets like Pluto, and countless smaller objects such as comets and asteroids. Each of these worlds has its own story to tell, and together they provide a window into the processes that shaped our solar system and others like it. The formation of the solar system. The solar system formed about 4.6 billion years ago from a cloud of gas and dust known as the solar nebula. This cloud, perhaps disturbed by a nearby supernova explosion, began to collapse under its own gravity, forming a rotating disk of material. At the center of this disk, the Sun ignited, while farther out, clumps of gas and dust coalesced into planets, moons, and other bodies. The inner solar system, where temperatures were higher, gave rise to the rocky planets, Mercury, Venus, Earth, and Mars. These planets are composed mostly of silicates and metals, and they have relatively thin atmospheres. In contrast, the outer solar system, where it was cooler, allowed gas giants like Jupiter and Saturn to form. These massive planets are composed mainly of hydrogen and helium, with small rocky cores deep inside. Farther out still are the ice giants Uranus and Neptune, which contain more ices like water, ammonia, and methane. The formation of the solar system was a violent process. Collisions between planetesimals, small, early bodies, were common, and the young planets were bombarded by comets and asteroids. This late heavy bombardment may have played a crucial role in delivering water and organic molecules to Earth, setting the stage for the emergence of life. Earth, the pale blue dot. Of all the planets in the solar system, Earth is the only one known to harbor life. It is a world of oceans, continents, and diverse ecosystems, all sustained by the Sun's energy and protected by a magnetic field and a thin atmosphere. From space, Earth appears as a pale blue dot, a fragile world floating in the vastness of space. It is our home, and for now, the only place in the universe where life is known to exist. Earth's unique characteristics make it a rare gem in the cosmos. Its distance from the Sun places it in the habitable zone, where liquid water can exist on the surface. Water, in turn, is essential for life as we know it. The presence of a large moon helps stabilize Earth's axial tilt, giving us relatively stable climates over long periods. The planet's magnetic field shields us from harmful solar radiation, and its atmosphere provides the oxygen we breathe and the greenhouse gases that keep the planet warm enough for life to thrive. Earth has not always been a hospitable place. For much of its early history, the planet was a molten ball of rock, bombarded by asteroids and comets. As it cooled, oceans formed, and the first simple life forms, bacteria and archaea, appeared in its oceans. Over billions of years, life evolved, eventually leading to the complex ecosystems we see today. Yet, as fragile as Earth appears, it is resilient. Life on Earth has survived multiple mass extinctions, ice ages, and dramatic shifts in climate. The story of life on Earth is a testament to the power of adaptation and evolution, and it serves as a reminder of how precious and rare life may be in the cosmos. Chapter 5: The Expanding Universe. The universe is not static. It is expanding, and it has been since the moment of the Big Bang. This discovery, made in the 20th century, revolutionized our understanding of the cosmos and raised profound questions about its origin, its fate, and our place within it. The Hubble expansion, a moving universe. In 1929, astronomer Edwin Hubble made a groundbreaking discovery: the universe is expanding. He observed that galaxies are moving away from us, and the farther they are, the faster they recede. This relationship, known as Hubble's law, provided the first direct evidence that the universe had a beginning, the Big Bang, and that it has been expanding ever since. The expansion of the universe means that space itself is stretching, carrying galaxies along with it. It is not that galaxies are moving through space, rather, space is expanding, causing the distance between galaxies to increase. This discovery has profound implications for our understanding of the cosmos. It suggests that the universe had a beginning, that it is evolving, and that it will continue to change over time. The expansion also means that, as we look farther into space, we are looking back in time. The light from distant galaxies has traveled billions of years to reach us, allowing us to see the universe as it was in its infancy. This look-back time enables astronomers to study the formation and evolution of galaxies, stars, and other cosmic structures, providing a window into the early universe. The role of dark energy. In the late 20th century, astronomers made a discovery that shook the foundations of cosmology: the expansion of the universe is not slowing down, as many had expected, but is instead accelerating. This revelation, confirmed by observations of distant supernovae, suggests that there is a mysterious force at work in the cosmos, a force that scientists have named dark energy. Dark energy is perhaps the most enigmatic component of the universe. It makes up roughly 68% of the total energy in the universe, yet we know almost nothing about it. Unlike dark matter, which exerts a gravitational pull, dark energy appears to have the opposite effect: it pushes galaxies apart, driving the accelerated expansion of the universe. This has profound implications for the future of the cosmos. The nature of dark energy remains one of the greatest unsolved mysteries in modern physics. Some theories suggest that it could be related to the vacuum energy of space itself, a consequence of quantum fluctuations on the smallest scales. Others propose that it might represent a new force of nature, one that operates only on the largest scales. Despite decades of research, we are still far from understanding what dark energy is and why it behaves the way it does. One thing is certain: dark energy will determine the ultimate fate of the universe. If the expansion continues to accelerate, the universe may end in a big freeze, where galaxies are pulled so far apart that stars burn out and the cosmos becomes a dark, cold, and empty place. Alternatively, dark energy could become stronger over time, leading to a big rip, where the expansion becomes so rapid that even atoms are torn apart. Understanding dark energy is crucial for answering these profound questions about the future of the universe. The fate of the universe, a philosophical question. The discovery of dark energy and the accelerating expansion of the universe forces us to confront difficult questions about the ultimate fate of everything. Will the universe continue to expand forever, or will it one day collapse back in on itself? Will the stars and galaxies we see today eventually fade into darkness, or will new structures continue to form? One possible outcome is the Big Freeze, a scenario in which the universe expands indefinitely. As galaxies move farther apart, the formation of new stars will slow down, and the existing stars will eventually burn out. Over trillions of years, the universe will become a cold, dark place, with only the remnants of stars, white dwarfs, neutron stars, and black holes, remaining. In this distant future, even black holes will eventually evaporate through a process known as Hawking radiation, leaving behind a universe that is essentially empty. Another possibility is the Big Rip, where the expansion of the universe accelerates to the point where even the strongest forces, gravity, electromagnetism, and the nuclear forces, can no longer hold matter together. In this scenario, galaxies, stars, planets, and even atoms will be torn apart by the relentless expansion of space. The universe would end not with a whimper, but with a catastrophic tearing apart of everything. A third possibility is the Big Crunch, where the expansion of the universe eventually reverses, causing galaxies to rush back toward one another. This would lead to a dramatic collapse, with all matter and energy being compressed into a singularity, a point of infinite density, similar to the state the universe was in at the moment of the Big Bang. Some cosmologists speculate that this cycle of expansion and collapse could repeat, with the universe going through an endless series of Big Bangs and Big Crunches. Each of these scenarios raises profound philosophical questions. If the universe is destined to end in darkness, what does that mean for the meaning of life and existence? If the universe is cyclic, does that imply an eternal recurrence, with the same events repeating over and over? These questions remind us that cosmology is not just a science of physical laws and observations, it is also a discipline that touches on the deepest questions of human existence. Chapter 6: The Search for Extraterrestrial Life. As we peer deeper into the cosmos, we are confronted with one of the most profound questions humanity has ever asked: are we alone in the universe? For millennia, people have speculated about the possibility of life beyond Earth. But it is only in the last few decades, with the advent of modern astronomy and space exploration, that we have been able to begin the search in earnest. The search for extraterrestrial life takes many forms, from the study of planets and moons in our own solar system to the search for signals from intelligent civilizations on distant worlds. It is a search that spans both science and philosophy, as we grapple with the implications of finding, or not finding, life beyond Earth. SETI and the search for intelligent civilizations. The search for extraterrestrial intelligence, SETI, began in earnest in the 1960s, when scientists first pointed radio telescopes at the sky, hoping to detect signals from distant civilizations. The idea behind SETI is simple: if intelligent civilizations exist elsewhere in the galaxy, they might be using radio waves or other forms of electromagnetic communication to reach out to the stars, just as we are. By scanning the sky for unusual radio signals, we might be able to detect the presence of another civilization. One of the most famous tools in this search is the Drake equation, a formula developed by astronomer Frank Drake to estimate the number of advanced civilizations in our galaxy that might be capable of communication. The equation takes into account factors such as the rate of star formation, the fraction of stars that have planets, the number of planets that could support life, and the likelihood that life will evolve into intelligent beings. While many of the terms in the Drake equation are still uncertain, it provides a framework for thinking about the possibilities of extraterrestrial life. However, despite decades of searching, no definitive signals from intelligent civilizations have been detected. This raises the question of the Fermi paradox: if intelligent civilizations are common in the galaxy, why haven't we found any evidence of them? There are many possible answers to this question. Perhaps intelligent life is rare, or perhaps civilizations tend to destroy themselves before they can develop the technology to communicate across the stars. It is also possible that extraterrestrial civilizations are deliberately avoiding contact with us, or that they are using forms of communication that we are not yet able to detect. Despite these challenges, the search for intelligent life continues. New technologies, such as the development of more sensitive radio telescopes and the ability to detect optical and infrared signals, are opening up new possibilities for SETI. The discovery of even the faintest signal from an extraterrestrial civilization would have profound implications, not only for science but for our understanding of ourselves and our place in the universe. Life in the solar system, Mars, Europa, and Enceladus. While the search for intelligent life focuses on distant stars and galaxies, the search for simple life forms, microbial life, has a more immediate focus, our own solar system. Over the past few decades, scientists have come to realize that several places within our solar system might have the conditions necessary to support life, even if that life is very different from what we are familiar with on Earth. Mars has long been a focus of the search for life. Once, billions of years ago, Mars had liquid water on its surface, and it is possible that microbial life could have arisen there during that time. Although the surface of Mars today is cold and dry, with a thin atmosphere that offers little protection from radiation, there may still be pockets of liquid water beneath the surface. Recent discoveries of methane in the Martian atmosphere, as well as seasonal variations in its concentration, have raised the tantalizing possibility that microbial life might still exist on Mars today. But Mars is not the only place in the solar system where life might be found. Two of Jupiter's moons, Europa and Ganymede, as well as Saturn's moon Enceladus, are covered in thick layers of ice, beneath which lie vast oceans of liquid water. These oceans are kept warm by the tidal forces generated by the gravitational pull of their parent planets, and they may contain the conditions necessary for life. In 2005, the Cassini spacecraft discovered plumes of water vapor and organic molecules erupting from Enceladus's south pole, suggesting that hydrothermal vents, similar to those found in Earth's oceans, might exist beneath the ice. Such vents could provide the energy and nutrients necessary to sustain life. Future missions to these icy moons, such as NASA's Europa Clipper and potential landers, will focus on studying the chemistry of these subsurface oceans and searching for signs of life. The discovery of even the simplest forms of life in our own solar system would revolutionize our understanding of biology and the conditions necessary for life. It would also suggest that life might be common throughout the universe, thriving wherever the right conditions are met. The ethics of contact: what happens if we are not alone? As we continue the search for extraterrestrial life, particularly intelligent life, we must also confront the ethical and philosophical questions that such a discovery would raise. What should we do if we detect a signal from another civilization? Should we attempt to communicate, and if so, how should we approach this monumental task? These are not just scientific questions, they touch on deep issues of ethics, responsibility, and our understanding of ourselves as a species. One of the most fundamental questions is whether we should attempt to make contact at all. Some scientists argue that the discovery of an extraterrestrial civilization could be one of the most dangerous events in human history. If we reach out to an alien civilization, we cannot predict how they will respond. They may be peaceful, curious explorers like ourselves, or they may be hostile. Given the vast distances involved, direct conflict may be unlikely, but even the simple act of communicating could have unintended consequences. In the 1970s, Carl Sagan and his colleagues sent a message into space on the Voyager spacecraft, in the form of the Golden Record, a collection of sounds and images meant to represent the diversity of life on Earth. This was a bold gesture, an attempt to show that we, as a species, are curious, peaceful, and eager to make contact. But there is no guarantee that an alien civilization would interpret our message in this way. The cultural, biological, and technological differences between our species and theirs could be so vast that meaningful communication might be impossible. Another ethical consideration is the potential impact on human society. The discovery of extraterrestrial life, particularly intelligent life, would challenge many of the beliefs and assumptions that have guided human history. Religions, philosophies, and ideologies would need to adapt to the realization that we are not the only intelligent beings in the universe. This could lead to profound changes in how we view ourselves, our place in the cosmos, and our responsibilities to one another and to other forms of life. In addition to these questions, we must also consider the possibility that we might one day visit or colonize planets where life already exists. If we discover microbial life on Mars, Europa, or another world, we will need to decide how to protect that life while still pursuing our scientific goals. Should we attempt to preserve alien ecosystems, or should we prioritize human exploration and colonization? These are not easy questions to answer, but they are questions we will need to confront as we continue our journey into space. Ultimately, the ethics of contact with extraterrestrial civilizations is a question of humility and responsibility. We must recognize that, as newcomers to the cosmos, we have much to learn and much to protect. Whether we are alone or not, the universe is a place of incredible beauty and complexity, and it is our duty to explore it with respect and care. Chapter 7: Humanity's Future in Space. As we stand on the threshold of a new era of space exploration, it is clear that humanity's future lies among the stars. The challenges are immense, technical, financial, and ethical, but the rewards are equally vast. Space is not just the next frontier, it is the ultimate frontier, one that offers us the opportunity to expand our knowledge, secure the long-term survival of our species, and perhaps even find new worlds to call home. Colonizing Mars, a new frontier. Mars, the fourth planet from the Sun, has long captivated the human imagination. It is a world both familiar and alien, with landscapes that resemble deserts on Earth but with an atmosphere so thin and cold that liquid water cannot exist on the surface for long. Yet, despite its harsh conditions, Mars is the most promising candidate for human colonization in the solar system. The idea of colonizing Mars is not a new one. Science fiction writers have imagined human settlements on the Red Planet for over a century, but in recent decades, these ideas have begun to move from the realm of fiction to the realm of possibility. NASA, SpaceX, and other organizations are actively working on the technologies needed to send humans to Mars and establish permanent colonies. The first step in colonizing Mars will be to send robotic missions to scout potential landing sites, study the availability of resources, and test technologies for producing water, oxygen, and building materials from the Martian environment. Once these technologies are proven, human missions can begin. The first settlers will face a daunting array of challenges, from surviving the radiation of deep space to finding ways to grow food in an environment where the soil is toxic and sunlight is weak. But the potential rewards are immense. A successful colony on Mars would provide humanity with a second home, a place where we could survive if Earth were to become uninhabitable due to natural or human-caused disasters. It would also serve as a stepping stone for further exploration of the solar system, opening the door to human missions to the moons of Jupiter and Saturn, and perhaps even to the asteroid belt and beyond. Mars colonization also raises profound ethical and philosophical questions. What right do we have to terraform another planet, altering its environment to suit our needs? Should we prioritize the search for life on Mars before we begin building settlements, to avoid destroying any potential ecosystems that might exist there? These are questions that we will need to grapple with as we plan for the future of human space exploration. Beyond Mars, venturing to the outer solar system and beyond. While Mars is the most immediate target for human colonization, it is by no means the only one. The outer solar system, with its gas giants, icy moons, and dwarf planets, offers a wealth of opportunities for exploration and, possibly, colonization. One of the most intriguing targets is Europa, a moon of Jupiter that is thought to have a subsurface ocean beneath its icy crust. This ocean could contain more water than all of Earth's oceans combined, and it is possible that life might exist in the dark, cold depths, sustained by hydrothermal vents similar to those found on Earth. Europa's potential as both a scientific target and a future outpost for human exploration makes it a prime candidate for future missions. Another potential destination is Titan, Saturn's largest moon. Titan is the only moon in the solar system with a thick atmosphere, and it has lakes of liquid methane and ethane on its surface. While Titan's surface is far too cold to support liquid water, its thick atmosphere and rich organic chemistry make it an intriguing target for the study of prebiotic chemistry, the chemical processes that lead to the formation of life. Some scientists have even speculated that Titan could harbor life forms based on methane or other exotic chemistries. Further afield, the asteroid belt offers vast resources for mining, including water, metals, and other materials that could support space-based industry. While living on an asteroid may seem far-fetched, future technologies could allow humans to establish colonies on these small, rocky worlds, using their resources to build habitats and fuel further exploration. Beyond the asteroid belt, the outer planets, Jupiter, Saturn, Uranus, and Neptune, and their moons offer further opportunities for exploration. While the gas giants themselves are not suitable for human habitation, their moons, such as Ganymede, Callisto, and Enceladus, could one day serve as outposts for human exploration. These moons contain vast amounts of water ice, which could be used to support human settlements and fuel space travel. Finally, as we look even farther into the future, we can imagine human missions to the Kuiper Belt and Oort cloud, the distant regions of the solar system where icy comets and dwarf planets like Pluto reside. These missions would take us to the very edge of the Sun's influence, providing a window into the formation of the solar system and the dynamics of planetary systems. The Voyager missions, humanity's message to the stars. In 1977, NASA launched two spacecraft, Voyager 1 and Voyager 2, on missions to explore the outer planets of the solar system. These spacecraft, still traveling through space more than 40 years later, have become symbols of humanity's desire to explore the cosmos. They are now the most distant human-made objects in the universe, having crossed the boundary of the solar system and entered interstellar space. The Voyager missions provided us with stunning images and data from the outer planets, revealing details about Jupiter, Saturn, Uranus, and Neptune that had never been seen before. But perhaps their most enduring legacy is the golden record that they carry, an audiovisual message from Earth, intended for any intelligent life that might one day find the spacecraft. The golden record contains sounds, music, and images from Earth, including greetings in multiple languages, the sounds of a heartbeat and a baby crying, and music from different cultures and times. It is humanity's message to the stars, a snapshot of our planet and our species at a particular moment in time. As Carl Sagan, who helped design the golden record, famously said, the spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. As the Voyagers continue their journey through interstellar space, they serve as reminders of humanity's desire to reach out into the unknown, to explore the cosmos, and to leave a lasting mark on the universe. They are symbols of our curiosity, our creativity, and our hope for the future. Terraforming, creating new Earths. One of the most ambitious ideas for the future of space colonization is terraforming, the process of transforming hostile environments on other planets into habitable ecosystems where humans can live without the need for artificial life support systems. The most immediate candidate for terraforming is Mars, due to its relative proximity to Earth and the presence of some resources like frozen water and carbon dioxide in its atmosphere. Terraforming Mars would involve a variety of methods aimed at warming the planet, thickening its atmosphere, and creating conditions suitable for liquid water to exist on the surface. One proposed method is releasing greenhouse gases, which could trap heat in the atmosphere and gradually raise the planet's temperature. Another idea involves redirecting asteroids or comets to impact Mars, releasing energy and materials that could further contribute to atmospheric thickening and planetary warming. However, the challenges of terraforming are enormous. Mars lacks a magnetic field to protect its atmosphere from being stripped away by solar wind, and the planet's low gravity would make it difficult to retain a thicker atmosphere over time. Even if terraforming succeeded in creating a breathable atmosphere, it would take centuries or millennia to transform Mars into a fully habitable world. Furthermore, the ethical implications of altering another planet's environment must also be considered, particularly if microbial life is discovered on Mars. Other candidates for terraforming include Venus, which would require cooling the planet and reducing its thick, toxic atmosphere, and Titan, Saturn's moon, where altering the methane-rich environment would present a unique set of challenges. These scenarios, while fascinating, remain distant in terms of technological feasibility. Terraforming represents humanity's boldest attempt to reshape other worlds in our image, but it also forces us to reflect on our responsibilities as planetary engineers. As we strive to create new Earths, we must also ensure that we protect the one Earth we already have. Chapter 8, A Cosmic Perspective, Our Place in the Universe. Earth as a Pale Blue Dot, continued. In Carl Sagan's reflection on the pale blue dot, he reminds us of the fragility of life on Earth, the interconnectedness of humanity, and the uniqueness of our planet in the cosmic context. This perspective forces us to confront the stark reality that, despite all our advancements and achievements, Earth is just a tiny speck in a vast, possibly indifferent universe. From this cosmic perspective, the divisions and conflicts that define much of human history seem trivial, even absurd. Borders, political ideologies, and economic systems, while significant in our day-to-day lives, fade into insignificance when viewed from the distance of the stars. The Earth is not just our home, it is our only home, and it is a responsibility we all share to protect it, cherish it, and sustain it for future generations. The pale blue dot also offers a sense of humility and wonder. The knowledge that we are part of something far greater than ourselves, that the universe is vast beyond comprehension, and that we are made of the same elements as the stars, this understanding deepens our connection to the cosmos. It reminds us that, although we are small, our existence is part of the grand tapestry of the universe. The exploration of space, therefore, is not just about expanding our horizons outward, it is also about looking inward. The more we learn about the universe, the more we realize how precious and fragile life is. Earth is a rare and beautiful gem in a universe that is mostly empty and hostile. The cosmic perspective reminds us of the importance of caring for our planet, the only known world that harbors life. The nature of life in the universe. The discovery of life elsewhere in the universe, whether microbial or intelligent, would represent one of the greatest scientific breakthroughs in history. It would fundamentally change our understanding of biology, evolution, and the conditions necessary for life. But even without direct evidence of extraterrestrial life, the study of extremophiles on Earth, organisms that thrive in extreme environments, has expanded our understanding of where and how life can exist. The diversity of life on Earth, from deep-sea hydrothermal vent communities to microbes living in boiling hot springs, suggests that life may be more adaptable than we once thought. These discoveries fuel the hope that life could exist in similarly extreme conditions on other worlds, perhaps beneath the icy crust of Europa or in the methane lakes of Titan. The search for life beyond Earth also forces us to consider the broader philosophical implications of life as a cosmic phenomenon. If life exists elsewhere, it raises questions about the nature of intelligence, consciousness, and the potential for communication across vast interstellar distances. What forms might alien life take? Would they share any common characteristics with life on Earth, or would they be completely alien in their biology, behavior, and thought? If we discover intelligent life, how would it affect our understanding of our place in the universe? Would it humble us, or would it provoke fear and competition? The potential for contact with extraterrestrial civilizations is both thrilling and daunting. It represents a new frontier in the exploration of life's diversity across the universe. The cosmos as our heritage. As we explore the stars, it is important to remember that the cosmos is not something foreign or distant, it is part of our heritage. The atoms that make up our bodies, the water we drink, the air we breathe, were all created in ancient stars that lived and died long before the Earth was formed. We are, quite literally, made of stardust. This realization, that we are part of the universe, deepens our connection to the cosmos. Our story is not separate from the story of the universe, it is intertwined with it. The birth of stars, the formation of galaxies, the creation of planets, all of these events are part of the same cosmic story that led to the emergence of life on Earth. As we venture farther into space, we are not just exploring new worlds, we are exploring our own origins. Each new discovery brings us closer to understanding where we came from, how we fit into the larger universe, and what our future might hold. The exploration of space is, in many ways, an exploration of ourselves. It is a quest to understand the forces that shaped our world and the possibilities that lie ahead. As we continue to learn more about the universe, we are also learning more about what it means to be human. The cosmos is our heritage, and it is our responsibility to explore it with curiosity, humility, and a sense of wonder. Chapter 9: The Future of Humanity in the Cosmos. As humanity stands on the threshold of a new era of space exploration, we are forced to ask ourselves deep questions about our future. Will we be content to remain on Earth, our cradle and sanctuary, or will we venture out into the cosmos to become a multiplanetary species? The answer to this question may determine not only our survival as a species but also our evolution as a civilization. The future of humanity in the cosmos is full of possibilities and challenges. Technological advancements will open doors to worlds we can only imagine, but they will also present us with profound ethical dilemmas. Will we, as Carl Sagan hoped, be wise enough to explore the cosmos with humility and respect, or will we repeat the mistakes of our past, exploiting and consuming without regard for the consequences? The necessity of space exploration. The challenges facing Earth, climate change, resource depletion, political instability, make it clear that the long-term survival of humanity may depend on our ability to expand beyond our home planet. While Earth is and always will be our home, it is vulnerable to both natural and human-made disasters. Space exploration provides us with the opportunity to diversify our habitats and ensure that no single catastrophe could wipe out our entire species. Mars, with its proximity and relatively favorable conditions, is the first step in this journey. But even Mars is only a stepping stone. The moons of the outer planets, asteroids rich in resources, and eventually exoplanets in distant star systems could one day serve as new homes for humanity. Space exploration is not just a matter of curiosity, it is a matter of survival. But beyond the practical necessity of space exploration lies a deeper reason for venturing into the cosmos: the drive to understand and to explore. Humanity has always been a species of explorers. From the first humans who crossed continents to the scientists who launched spacecraft to distant planets, we have always sought to push the boundaries of the known world. Space exploration is the next frontier in this journey, offering us the chance to learn more about the universe and our place within it. Becoming a multiplanetary species. The process of becoming a multiplanetary species will not be easy. It will require the development of new technologies, the establishment of permanent colonies, and the ability to sustain human life in environments radically different from Earth. But it is a goal worth striving for. The first steps toward this future are already being taken. Space agencies like NASA, along with private companies like SpaceX, are working to develop the technologies necessary for human missions to Mars. These missions will be the first in a long line of efforts to establish a permanent human presence on other planets. Mars offers unique challenges and opportunities. Its gravity is lower than Earth's, its atmosphere is thin, and its surface is cold and dry. But it also has resources, water ice, minerals, and solar energy, that could be used to support human life. Future Martian colonies could be built underground or within domes to protect settlers from radiation and the harsh climate. Over time, the technology to terraform Mars, transforming it into a more Earth-like environment, could be developed, though this remains a distant possibility. Once humanity has established a foothold on Mars, the outer solar system beckons. The moons of Jupiter and Saturn, particularly Europa and Enceladus, may harbor subsurface oceans that could support life. These moons, along with the asteroid belt, offer abundant resources that could fuel further exploration and settlement. In time, human colonies could spread across the solar system, creating a network of worlds connected by space travel and commerce. Becoming a multiplanetary species is not just about survival, it is about growth, adaptation, and evolution. As humans spread across different planets and environments, our species will inevitably change. Different gravitational forces, climates, and ecosystems will shape new human societies, cultures, and even biology. The future of humanity may be as diverse and dynamic as the universe itself. The role of artificial intelligence in space exploration. As we venture deeper into space, we will increasingly rely on artificial intelligence, AI, to assist us in exploration, research, and survival. AI will play a crucial role in the development of space colonies, helping humans navigate the complexities of life in space and manage the challenges of long-distance space travel. AI systems are already being used in space exploration to analyze data, navigate spacecraft, and operate robotic explorers. In the future, AI will assist in more complex tasks, from the construction of habitats on distant worlds to the management of life support systems. On long-term space missions, AI could help monitor human health, make scientific discoveries, and even perform maintenance and repairs. As AI systems become more advanced, they may also play a role in the search for extraterrestrial life. AI can process vast amounts of data far more quickly than humans, making it an invaluable tool in the analysis of signals from distant planets and stars. In the search for life beyond Earth, AI could help us detect subtle signs of life that would be difficult for human observers to identify. However, the increasing reliance on AI also raises ethical and philosophical questions. What happens if AI systems become more autonomous and capable of making decisions without human oversight? How do we ensure that AI is used responsibly and ethically in space exploration? These are questions that will need to be addressed as AI continues to evolve and play a larger role in our exploration of the cosmos. The ultimate fate of humanity. The ultimate fate of humanity is inextricably linked to our relationship with the cosmos. As we venture beyond Earth and explore new worlds, we are not just ensuring the survival of our species, we are also shaping our future identity. The decisions we make in the coming centuries will determine the trajectory of human civilization for millennia to come. In one possible future, humanity becomes a multiplanetary species, spreading across the solar system and eventually reaching distant stars. We establish thriving colonies on Mars, the moons of Jupiter, and beyond. New technologies allow us to travel faster than the speed of light, making interstellar exploration a reality. In this future, humanity thrives, expanding its reach across the galaxy, discovering new life forms, and unlocking the mysteries of the universe. In another possible future, humanity remains confined to Earth, struggling to address the challenges of climate change, resource depletion, and political conflict. Space exploration becomes a distant dream, and humanity's potential is never fully realized. This future is one of stagnation and decline, where the vastness of the cosmos remains forever out of reach. The choice between these futures is ours to make. The challenges we face are immense, but so too are the opportunities. The universe is vast, and it is waiting for us to explore it. Whether we succeed or fail in this endeavor will depend on our ability to work together, to innovate, and to approach the cosmos with the same sense of wonder and curiosity that has always driven humanity forward. Conclusion: the eternal journey. As we conclude our exploration of the cosmos, we are reminded of the words of Carl Sagan, who once said, "Somewhere, something incredible is waiting to be known." The universe is a place of endless mystery, beauty, and possibility. It is a place where the laws of physics and the forces of nature have conspired to create galaxies, stars, planets, and, ultimately, life. The journey into space is not just about science or survival, it is about understanding who we are and what our place in the universe truly is. We are the products of billions of years of cosmic evolution, the descendants of stars that lived and died long before our solar system was born. And now, as we venture beyond Earth, we carry with us the legacy of those stars, the hopes of our ancestors, and the promise of future generations. The universe is vast beyond comprehension, but within that vastness, we find meaning. We are explorers, creators, and seekers of knowledge. The journey ahead will be long, challenging, and full of uncertainties, but it is a journey worth taking. As we look up at the night sky and contemplate the stars, we are reminded that the universe is not just something we observe, it is something we are a part of. The story of humanity and the story of the cosmos are intertwined, and as we continue to explore the universe, we will write new chapters in that grand narrative. The future is unknown, but the possibilities are infinite. The journey continues, and it is one that will take us to the stars and beyond. Thank you for being a part of this cosmic journey. If you're as fascinated by the universe as we are, make sure to subscribe to the channel to stay updated with the latest videos about space exploration, cosmic mysteries, and humanity's future among the stars. Don't forget to like this video if you enjoyed it, and feel free to share your thoughts in the comments. What part of the universe are you most curious about? Engage with us by sharing your ideas and asking questions. Your curiosity helps us explore deeper into the wonders of the cosmos, and your feedback shapes the content we create for this incredible community of space enthusiasts. Together, let's explore the mysteries of the universe, one video at a time. So, hit that subscribe button, tap the notification bell to never miss an update, and let's continue this cosmic adventure together.